I work in the evaluation section at ECMWF, but I've also been sitting on the steering group for the Polar Prediction Project, WWRP steering group, which is sort of been planning YOPP. And the ECMWF involvement goes back even further, because I think Peter Boer, who was our Deputy Director of Research, was actually kind of an original member of this steering group for the PPP. And most of what I'm going to talk about now are a few sort of highlights in terms of what we're doing. And most of this is going on under the framework of this EU project called Applicate, which is sort of focused on polar predictability and prediction, as well as linkages to mid-latitudes, which is a major theme of that project. And this is led by Thomas Jung, who's also the chair of the Polar Prediction Project Steering Group, and was sort of funded in support of, specifically in support of YOPP. So that's me and my background, but just to say a little bit about what we're doing at ECMWF for orientation, in case you're not familiar with what we do. So we're an operational weather forecasting center, and we're producing forecasts twice a day. We're a global forecasting center, and if you look at this schematic on the, as well as providing the seasonal forecast, and if you look at this schematic on the right, I just want to mention a couple of developments which make YOPP particularly timely for us, and that's that we're now that we recently in the last cycle switched to having a dynamical sea ice model in our forecasts at all time ranges. So cryospheric processes are now pretty important to us, I would say, and so obviously trying to find opportunities for evaluating and improving the physics in those components is quite important. And we're also as part of Applicate, specifically implementing a multi-layer snow scheme, which we're hoping will improve the representation of the winter boundary layer in polar regions as well. Okay, so I'm going to go through a few highlights, and one of the big issues for us is sort of highlighted in this. The big questions for us is sort of highlighted in this time series here. So this is a time series of our skill scores through time. So it's the anomaly correlation. The red line is for the North Pole, so this North Pole region, which is north of 65, and then the blue curve here is the Northern Hemisphere. Is for the whole Northern Hemisphere, and you can see that because the red line is somewhat higher than the the red line's the Northern Hemisphere, the blue line's the pole, and you can see that because we've got a higher anomaly correlations in the Northern Hemisphere as a whole than we do in the Arctic, and this has been actually fairly consistent over time. So forecast skill in both areas is increasing, but the polar region, but the Arctic in particular, seems to always has slightly lower skill. And we'd like to sort of, we want to know how this is, and you can see on the right here. This is the case from these maps of root mean square error as well. You can see that the Arctic sort of has these dark red values compared to the lighter values in the mid latitudes. So one of the challenges for NWP in the Arctic is this sort of well-known sparse density of observations. So in the bottom panel here, you can see the distribution of synop conventional observations at the surface. So we have a very good sort of coverage over land and in the sort of in the North Atlantic and the Pacific, but actually there's quite a big hole in the in the Arctic itself. This is not the case for the satellite observations in the top here. So actually in the Arctic, because of the orbital configuration, we actually get a very good sampling in terms of passes over the Arctic from satellites. But obviously there's well-known issues in terms of actually interpreting, like particularly microwave data in the Arctic. And so we've been, computer's frozen. So one of the things that we've been doing as part of Applicate and in support of YOPP is doing these observing system experiments. So we want to assess effectively what the value is of the Arctic observing system for NWP. And so what we've done is so you can see here the sort of the footprint of polar orbiting satellites. And what we've been doing is taking out the polar regions. So we've run a series of experiments where we take out different observation types, north of 60 north and then south of 60 south, and then looking at what the impact is on forecasts, both in the polar regions and in the mid-latitudes. Okay, so we've run quite a few of these. So we've focusing on we've run one of these for summer and one of these for winter. So denying in turn microwave observations, infrared observations, conventional observations, GPSRO, polar AMVs, as well as running some special experiments where we deny just the extra observations that were taken during the YOPP SOPs. And these have been run for 4 months each, across a winter and a summer season. And this winter season contains the first YOPP SOP. We're also running. I should mention now that we're also running these experiments for this summer just gone during the second YOPP SOP, but we haven't had a chance to analyze the data from those experiments yet. Okay, so these are some of the results from the summer OSSE. OSSE stands for Observing System Experiment. So basically, each one of these lines on the right here corresponds to a different observing system experiment where a different observing type has been denied. You can see in the key here the various types. And effectively, one of these lines having a number greater than 0 means that there's been some degradation in the forecast skill as a result of denying the data. And in this, and we have the sort of the lead time at the bottom here. And what you can see is that this microwave, so in the Arctic, so on the panel here is the forecast skill in the Arctic itself. So you can see that the microwave observations have the strongest impact, certainly over the first few days, the forecast, but the conventional and the infrared satellite, so by conventional, I mean the radiosondes, surface pressure observations, reports from aircraft, etc. All of those are denied together, but it's really the microwave that's having the largest impact in the Arctic itself in summer. So and then on the left here, we've made, this is exactly the same type of plot, but this is just for the mid latitudes. So it's for the whole, the entire hemisphere, but just between 20 and 60 north. And you can see that rather than the case in the Arctic, where the error or the change in error peaks at over the first few days, in the mid latitudes, it's actually the difference actually takes some time to propagate out. So these errors they initially start, we're creating these additional forecast errors in the Arctic itself, and then after some time they propagate out of the Arctic, and then these additional errors actually affect the forecast in mid-latitudes. These are the same plots, but for winter. And then on the right here for the scores in the Arctic, you can see that in winter it's actually the conventional observations which are having the most impact. And the impact that they have seems to be largely constrained to the first couple of days. So after day 2, within the Arctic, there doesn't actually seem to be that much of an impact. And again, you can see that there's some impact in the mid-latitudes at slightly longer lead times. Okay, so these are the spatial maps of these impacts at various lead times. So from left to right, day 3, day 4, and day 5. And you can see that in summer we have these quite large impacts over North America at day 3 and day 4, and then also potentially at day 5, an area over sort of southern Europe, over the Iberian Peninsula, and the eastern part of the North Atlantic, where there seems to be some significant impact as well. And this hatching is where the hatching indicates where the degradation in the skill from the observing system experiment is significant. So you can really see that there's an impact not just in the Arctic, but in the mid-latitudes as well. In the winter, these spatial maps for the conventional observations are showing us that there's actually the area where there's a significant impact in the mid-latitudes is actually over Northern Asia. And so we're getting sort of a slightly different picture about the pathways through which errors in our forecast within the Arctic are actually communicated out to the mid-latitudes. Okay. So the second thing that we're working on here is that we're participating in this YOPP Site Nip, which stands for the YOPP Supersite Model Intercomparison Project. So this is an intercomparison of NWP forecast systems, but focused at polar supersites. So anywhere where there is detailed observations that would enable us to do process-based evaluation of model performance. So we're focusing initially on supersites at fixed locations. So you can see here in the north, in this map on the left that we have sites that are sort of capturing a range of different climate types within the Arctic. We have sites in North America, Europe, the European sector, as well as the Russian sector of the Arctic. And effectively, we've got a number of centres agreeing to participate in this. So as well as us, there's the UK Met Office, Russian Hydromet, and Environment and Climate Change Canada have all agreed to sort of signing up to provide model output, and the ISOA team and particularly colleagues at NOAA are contributing to this in a very important way by making these merged observatory data files. So one of the largest challenges in terms of actually doing this sort of evaluation at different sites is the fact that all of the data generally gets stored in different formats, which makes it very hard to do sort of routine verification and evaluation of many sites. And so this, I think that these merged observatory data files are actually going to be one of the most important legacies of this. And all of the data from this project is going to be hosted by Met Norway, who are also a partner in Applicate. And just to give you an idea of the type of thing that we might sort of look at, this is an example of the type of work that we're doing here at Sodankylä. So at the start, which is a super site in northern Finland, and on the top left here, you can see that basically the red colors here show the biases in our model. So the dark reds are wherever the sort of nighttime 2 meter temperature bias creeps up above 5 degrees. And one of the reasons that we think that this is occurring is because we currently, in our operational model, have a single layer snow scheme, which is not particularly responsive to transient changes in surface forcing. And at Sodankylä, there are very detailed temperature and surface energy balance measurements, and the temperature measurements are both on this tower, which is pictured, as well as through the snowpack and the soil. And so on the right here, I've plotted the temperatures. So in blue, we have the temperatures through on the mast. So it's height going in the top panel, and then in this bottom panel, these are temperatures going through the snow on the top section, and then the soil. And you can see that and then we've got our two versions of our model. So one with the green line here is the one where we have a multi-layer snow scheme, and then the red one here is where we've incorporated this multi-layer snow, and you can see that actually the surface is cooling down and we're getting something a little bit more realistic in terms of the very near surface temperatures. But also we're sort of managing to get sort of something which looks fairly reasonable in terms of the temperature profile through the snow as well. And this is the kind of thing that we're envisaging looking at as part of this YOPP Site Nip. So the third main contribution of ECMWF to YOPP is making a forecast data set available. So we're making our operational ensemble forecasts, sort of control run, available, so open access. And one of the nice things about this is that we've added some additional diagnostics. So this was done as part of the Year of Tropical Convection data set as well. But what it enables us to do is that we're adding additional process-based tendencies to the diagnostics, and effectively, you can look at differences in the you can sort of by looking at the tendencies, for example, for temperature, you can, as shown here. You can really say a lot about how the different climate regimes are behaving and what the important physics are. So these tendency plots are from a paper by Thomas Young from a couple of years ago, and you can effectively you can see the contribution of different processes to the to changing temperatures in the forecast. So you can compare the tropical ocean here, where so basically on these plots, each of the contributions of the different processes are in a different color here, and then if this curve is on the right hand side of the zero line, it means that this particular process is warming the atmospheric column at a particular layer. And if it's on the left-hand side, that it says that it's cool, it's telling you that the process is cooling that particular point in the atmosphere. So if you compare the tropical oceans, for example, where convection is really the dominant heat source in the atmosphere, to the Arctic, the sea ice covered ocean in winter, you can see that actually compared to the tropics where convection is really the dominant heat source, actually in the Arctic it's really the dynamics here in black. So this is, you know, effectively warm air being convected from lower latitudes by the dynamical processes within the model. And so you can start to look at these types of you can start to look at these sorts of physical processes in the Arctic with this sort of data set. Okay, so just in summary then, so we're working on developing a few sort of physical process models, so snow and sea ice in particular, working on trying to improve the usage of observations in data assimilation. We're providing this YOPP data set, developing diagnostics and verification, but also looking at these sort of observations and their impact to try and sort of assess the importance of the Arctic observing system. Okay, all right, I'll leave that up.
All right, thank you very much, Johnny. Thanks for the presentation and the overview of a variety of activities here. Are there questions from the group?
Yeah, this is David Bromwich here. Johnny, I'd like to ask you about a surprising result of the propagation of the impact into the mid-latitudes. Could you go back to that slide?
This one.
Yeah. So microwave in summer at 72 hours and 96 hours. So I'm going to ask you the obvious question. You've focused on the Northern Hemisphere. What in heaven's name is happening in Antarctica?
I mean, effectively, what we're finding is that these sort of you get these sort of small scale errors, and then they just propagate along, you know, sort of stationary wave structures. And so I'm guessing that in this particular season, the stationary wave structures would have been, you know, just right for you to get that propagation. I mean, does that look like the sort of thing that you'd expect anyway, Dave?
Well, it's JJA, so it's summer in the Northern Hemisphere and winter in the Southern Hemisphere. So I'm not sure. Maybe. It's quite
I was wondering whether you'd pick up on it.
You've got this, that's the biggest signal that you've got on planet Earth by the looks.
Yeah. Yes. No,
right,
I think there's actually quite a lot to be looked at in the Southern Hemisphere, which we haven't had a chance to yet. So,
do you think it might work the other way? You know,
in terms of,
you know, if there was, let's say you took all the microwave radiances out over south of 60 south, do you think it would propagate into the Northern Hemisphere?
yeah, maybe. I think trying to determine the sort of the dominant part. Yeah, I think doing these denials in the lower latitudes and then looking at the opposite impacts would also be quite interesting, but they're quite expensive.
Okay, that's it from me.
Yeah.
Thank you. Are there other questions?
Sorry, I was just going to say, if you've got any ideas for something to look at, Dave, then let me know.
Okay.
Sorry.
That's all right. That's no problem. Other questions for Johnny?
So this is Hailong Wang from PNL. I just have a quick question about, do you also provide, I guess not for aerosol, but do you also provide aerosol products for YOPP cloud products?
Yeah, so our kind of coupled aerosol sort of air quality forecasts are not included in the CAMS forecasting system isn't included in this YOPP data set I mentioned. So I don't think there are any aerosol fields in what we're providing online.
But you do have cloud products.
Yeah, so the cloud, fraction, and I'm sure will be in there, and other sort of macrophysical properties.
Okay, all right. Thank you.
Thanks, Hailong. Other questions? Johnny, I have a quick question. So for the second activity, the MIP, are there specific kind of comparison activities planned already? I know you showed an example of the kind of snow layer and surface layer measurements and the type of analysis that you're doing with that, but are there kind of atmosphere specific comparisons planned from that activity, or is it still kind of in the setup stage at this point?
I think basically what we're sort of at the stage where we've got, we're producing the data, but I think currently there's not really any, I think because there are so many sites that we're sort of providing data for, I think we'll effectively start to look at just one and do sort of focus the sort of first intercomparison activities, potentially at Sedancula, because we have a lot of, because we already have the data there and things are set up, but potentially for Barrow as well. I think Taniel's quite keen that we sort of do. I think they're focusing their production of these merged observatory data files on the ARM sites, basically. So I think potentially Sedancula and the ARM facilities will probably be the first ports of call in terms of the sort of multi-model analyses.
Sure. Okay. Yeah, that's. I mean, I'll advocate for those sites as well. So happy with that.
Yeah. Well, I'm interested to hear what you've got in your presentation. I'm wondering if there's some. Obviously, we'll be providing model data for this campaign period that you've just done. So.
Yeah. Exactly. All right. Any other questions? Okay, if not, I guess I'm up next. So this is my first IARPIC presentation, actually, I believe, but I'm going to give an overview after I share my screen. So I think, Johnny, you have to stop sharing for me to start sharing.
Yes, it's a red button at the top of the screen.
All right, so now I will share my screen and start the presentation. All right, is everyone able to see that all right?
Yes.
Okay, great. And I'm guessing, are you also seeing the box of controls at the top, or is that not present in your screen?
I do not see it.
Okay, excellent. All right, so I'm going to give an overview of a campaign that was recently completed called Profiling at Oliktok Point to Enhance YOPP Experiments, or POPEYE. This is a campaign that was completed by the Department of Energy ARM program, and I was the primary PI for this project, but it involved a wide variety of different participants, as you can see on the screen here. Just as a very quick introduction, the main purpose for the campaign is to provide a really detailed look at the lowest part of the Arctic atmosphere over the second special observing period, so basically July 1st through September 30th. And this is something that we were doing using a combination of increased radiosonde frequency, so launch frequency, and use of unmanned aircraft and tethered balloon systems. And so many of the measurements that I'm going to be discussing are focused kind of on the lowest kilometer or so of the atmosphere. The picture you see in the center here is one from the rooftop deck of the Oliktok Point facility. So this is a ARM mobile facility, very well instrumented observational site. And while not everyone necessarily is familiar with the ARM site, for some reason my slides, there we go, are not advancing. The Oliktok Point site, I think people may be slightly less familiar with than the site in Utgafik, or formerly Barrow. But you can see the two of them on the map here on the top left of the screen. The blue dot is Utgafik and the orange dot is Oliktok Point. Both are coastal sites, and specifically at Oliktok Point, the site is located only a few hundred meters from the coastline, and you can actually see in the top right figure here, again taken from the roof deck, you can barely see the water just in the top of the figure here. You also see this orange or this red tethered balloon system that was preparing for a launch on this given day. A couple things to note about Oliktok Point. So one is the presence of the third ARM mobile facility, and this includes a variety of instruments, which you can see listed on the right-hand side of the screen here. I won't go through all of them, but there are a variety of sensors related to retrieving information on clouds, thermodynamic profiles, wind profiles, radiometric quantities, surface meteorological properties, aerosols, and gases. The other interesting thing about Oliktok Point, and part of the reason that this specific campaign was really focused at this site, is that there is access to airspace, and this includes one area of restricted airspace that's centered over the geographic point. On the bottom left here, you can see kind of the coastline. This is the actual Oliktok Point, and the orange dot is where the mobile facility is sitting. The red circles here indicate the extent of restricted airspace that the Department of Energy can activate for aerial activities such as the ones that I'm going to talk about. And this limits access or restricts access to that area for other aircraft and provides a safe opportunity for conducting unmanned aircraft and tethered balloon missions. The second area of airspace that I'm not going to talk much about here is the offshore warning area, W220. This extends to 82 North, but this was not leveraged for this POPEYE campaign. So at a very high level overview here, this is a kind of a calendar perspective of what the POPEYE campaign was intended to look like. So you can see that over time, as we start in July, the tethered balloon system here indicated by TBS and the Data Hawk, which is an unmanned aircraft system, we're going to be alternating windows, time periods for sampling, roughly 2 weeks at a time. Those crews would be up in the field, and again, they'd be alternating on a schedule that allowed them to have a little bit of overlap day to do intercomparison flight activities. And then radiosondes, we changed the frequency from the normal 2 per day frequency, and at the AMF3, the normal launch times are 9:30 roughly and 3:30 local to correspond with the 6 p.m. and midnight UTC launch times. We added a third launch daily at 9:30 p.m. local time or 6 a.m. UTC. The only window that was not scheduled to have any sampling was kind of this late August, early September window, just due to budgets and crew availability and things like that. As far as flight patterns go, this bottom left panel indicates the flight pattern that we had generally assigned to the tethered balloon. And so this is, of course, very idealistic because weather and other things impact operations. But the idea was to have an ascent up to whatever the maximum possible altitude for the balloon was given the weather conditions. And generally that was somewhere between, I would say, 500 and 1,000 meters, some days a little bit higher, some days a little bit lower. And then hold altitude at a given height for some amount of time, do a descent down to a given layer and back up. And this is something that could be carried out both in clear and cloudy conditions. The tethered balloon is able to fly through clouds without concern for icing for the most part. On the UAV side, we had 2 different flight patterns. For clear days, it was kind of nearly continuous profiling from 20 meters to the, again, maximum allowable altitude. On clear days, that was around 1,000 meters. And so you'd conduct multiple profiles before needing to change batteries and just repeat that for several flights over the course of a day. With cloudy conditions, we changed the profiling up a little bit, where we again profiled up to the cloud base for one flight, and then had a second flight where we'd try to hold altitude just below the cloud base in order to gather statistics on things like the covariability of vertical velocity and temperature structure around the cloud base. So a quick description of the platforms that we deployed here. The first is the DataHawk 2. This is a small, roughly 1 meter unmanned aircraft system that was developed at the University of Colorado and is currently operated by both CU and the DOE ARM program. These are relatively inexpensive systems, capable of flying for roughly an hour, a little bit more, again, depending on how they're flown and the conditions. And in terms of measurement capabilities, the DataHawks have a variety of sensors on board, mainly for thermodynamic measurements. So this includes fast and slow temperature measurements, the fast being on the order of several hundred hertz through the use of a fine wire. It also has relative humidity measurements, pressure, of course. We blend a variety of measurements to come up with a 3D wind vector estimate, and this is something that we're currently spending a lot of time to try to improve the reliability of. It also has sensors on board to measure the IR temperature of the surface in the sky, and then of course its position. This gives you an idea of the scale. It's me standing in the background with the DataHawk in front of me. And this is an aircraft that has been operated at Oliktok Point many times at this point. This is a platform that we've used in the past to study a variety of science topics. I'm just giving an example here of one related to the boundary layer structure. And this is specifically from a case where we had a very nice stable boundary layer. You can see we had fairly clear skies in this day. The top left picture is from the aircraft itself. You can see the nose just sticking into the right side of the picture. We were conducting kind of routine, regular profiling of this stable boundary layer day in order to look for some specific features that were brought out in a paper by Peter Sullivan, in which he showed in modeling work that you have these kind of sharp temperature gradients within the stable boundary layer that propagate through the model domain. And we were trying to conduct kind of very slow ascent-descent pairings to try to detect similar features. And in fact, the bottom right figure here is from the aircraft, and you do see some of these features, especially here, about 100 meters, kind of propagating their way through the atmosphere over the time that we were sampling. Each of these profiles is offset by 3 Kelvin in order to separate them from one another. There wasn't that much actual variability, clearly, during the course of the day. Now talking a little bit about the tethered balloon system. ARM operates a couple of different tethered balloon systems, and the picture on the left is one of the POPEYE flights from September when I was at Oliktok Point, and you can see the balloon itself with the tether and some of the payload underneath it. The figure in the center here with the red balloon and some of the markings on it indicates kind of an idealistic version of what the layout of the balloon may look like for a given flight. Generally, the balloon for POPEYE was set up to carry a variety of instruments. This included thermodynamic measurements from intermet instrumentation, and you can see we would have those positioned at various points on the tether. A distributed temperature sensing system that is indicated by the blue line here. This is a fiber optic cable through which we can detect very high resolution temperature measurements along the length of the tether during flight. Additionally, we had sensors for cloud microphysics, so some vibrating supercooled liquid water content sensors that would have a vibrating wire, and the oscillation of that wire changes, the frequency of oscillation of that wire changes with ice accumulation on the wire. And this is another sensor that we were flying in order to gain information on the cloud microphysics and macrophysics. And then a couple of different instruments related to aerosol measurements. We had a condensation particle counter, which is looking at particles between about 0.01 and 1 microns, and then a printed optical particle spectrometer, which is, again, an instrument that can provide us information on the size distribution of particles, in this case between 0.15 and 3 microns. And typically, we would try to stagger some of the aerosol instrumentation. So we would put some space in between the two different POPs instruments that are flown, for example, in order to be able to get more detailed profiles through the whole column and, for example, above and below a given stratiform cloud layer. And this is an example of data, not from POPEYE, but from a previous campaign where we have a few different panels here indicating the relative humidity in the top, the temperature, the POPs particle concentrations, and the CPC particle concentrations along the flight path. So the dots, the points indicate the flight path of the balloon. Also indicated are the ceilometer detected cloud base altitudes in the orange lines, and then radar reflectivity in the gray shading. This is one case that I've had a lot of interest in because this is a decoupled stratiform cloud case, and what we see is one, as you might expect, you see a decrease in aerosol concentration within the cloud layer because you have activation of the aerosol particles in the cloud droplets. You also see elevated aerosol layer, an elevated aerosol layer above the cloud. And over time, this is of great interest to me, you see this below cloud layer actually transition from one that it's fairly uniform and relatively low concentrations to one that has kind of an accumulation of particles below the cloud base. And we think this is likely related to evaporation and sublimation of water and ice from the cloud layer below the cloud. All right, some challenges faced during the campaign. It is the Arctic. Things never go 100% according to plan. One of the challenges is wildlife, and the picture on the left there is one that I took using a scope while I was up there. We had frequent, actually, bear visits, both brown bear and polar bears. And this, of course, puts a bit of a damper on operations. We have to get everybody inside and to safe locations. In addition, we had some weather issues. Icing and winds are always a concern. And then we had some technical challenges related to the presence of an Air Force radar system that went through some upgrades over the course of the campaign, which resulted in some interference issues with some of our sensors. So with those challenges, this is what our actual operations ended up looking like over the course of the campaign. If you remember the previous calendar, everything had kind of uniform colors. Now I've split it up into flight days and non-flight days, where the dark green indicates days where we did fly specific platforms, and the light green indicates days where we did not. Most notably, you can see the first Data Hawk campaign went very well. We had a lot of flights, a lot of data collected. When the crew came back for their second campaign, there were very substantial issues related to the interference with the radar, which ultimately ended up in the grounding of the Data Hawks for the rest of the campaign, which is unfortunate, but necessary for safety reasons. And so you see some of these darker, or these longer light green areas, those are related to that. Everything else, the other kind of on-off cycles are related to weather and wildlife. And so you can see for the radiosondes specifically, I have 3 different characterizations here, 1, 2, or 3 sondes on any given day. The operators did their best to launch 3, but sometimes high winds or the presence of wildlife prevented them from doing so. Looking at this differently, this is the time height cross section of all of the different flights and launches conducted. So the black lines are radiosonde launches, the blue lines are tethered balloon flights, the red lines are Data Hawk flights. And you can see the campaign started out very strong. The first month had very solid coverage. Moving into the second and third months, the absence of the Data Hawks really becomes notable. We did still get quite a few tethered balloon flights in during that window. All in all, there were 238 radiosondes launched during the campaign, 32 tethered balloon flights, which is almost 122 flight hours, and then 74 Data Hawk flights, mainly in the first half of the campaign, accumulating to about 64 flight hours. Some quick looks at some of the data. So this is looking at some 2-dimensional histograms of the radiosonde measurements. On the left, this is a temperature height distribution. And you can, I'm not going to go into too many details here, kind of an interesting bimodal split in the stratosphere. Again, I haven't gotten a chance to actually go very deep into any of this, but something we'll probably look at soon. Wind speed has kind of a shape that you might expect with a max near the tropopause. And then I also looked at the distance traveled from the Oliktok point site as a function of altitude. And so you can see that over, in the lower atmosphere up to 5 kilometers, most of the radiosondes were within 10 kilometers of the site itself and stayed close to home. As you go up in altitude, of course, things start to drift a little bit farther away, but for the most part, things were within 50 kilometers of the site. Looking at the other platforms here on the left, the map shows the locations of the Datahawk flights. The distribution on the bottom left shows the number of times the Datahawk sampled a given altitude. Same plot on the right-hand side for the tethered balloon. The blue points again are the location of the balloon. You can see a little bit of an issue with the GPS measurements, again, likely related to the Air Force radar here. The balloon did not travel that far offshore during the campaign. That's just an interference issue. And again, on the bottom right, you see the probability distribution of altitude sampled. The balloon tended to hang out at given altitudes more, so you kind of see more of these peaks within the data set. And then the center shows the different temperatures sampled by the two systems as a function of altitude. Again, first cut at the data. This has been, I would say, minimally quality controlled, but it gives you an indication of the types of conditions that were sampled. And specifically, again, you see the Datahawk temperatures typically above freezing. This is earlier on in the campaign, whereas the tethered balloon sampled a wider variety of conditions. So in summary, we conducted a variety of different activities at the Oliktok Point site during the second special operations period for YOPP. This included additional radiosonde launches, unmanned aircraft flights, and tethered balloon flights. The campaign resulted in the launch of 238 radiosondes, 32 tethered balloon flights, and 74 Datahawk flights. And despite some of the challenges that we ran into, POPEYE is going to provide a fairly unique data set, I would say, offering really enhanced perspectives on the structure of the lower atmosphere, primarily from a thermodynamic and dynamic perspective, but also in terms of some of the aerosol properties and cloud properties that were collected with the tethered balloon system. And so in conjunction with the measurements from the AMF3, which is also co-located at Oliktok Point, I think that the campaign offers a terrific opportunity for the development of process understanding and also for perhaps parameterization development and some kind of close collaboration with modeling centers to really do a detailed once-over of the boundary layer structure in the model over this time period. All the data will be available on the ARM archive. I think many of the data sets are already there. Some are still in processing. And we are very close to submitting a data publication on this campaign, which will be submitted to Earth System Science Data. Hope to have that submitted in the next few weeks. And with that, I'll acknowledge funding sources, primarily the DOE ARM program, the DOE Atmospheric System Research Program for some of our time, and NOAA as well. And I will stop there and take any questions. If there are any.
Gijs, can I ask whether the radiosonde ascents went out over the GTS?
Yeah, you of course you can. So the short answer is they should have. And Jim Mather's on the line, I believe. I know about 2 years ago there was some discussion about challenges with some of the formatting of the buffer files for the ARM radiosondes from Oliktok and Barrow, and it wasn't clear whether they were all being ingested appropriately or not. But I believe that Donna Holdridge and others had worked to fix that. Jim, I don't know if you have any further insight on that.
I think he had to drop off.
All right, so it's possible we lost Jim. But I think the short answer is I think so, Dave. Okay. It's always a tricky one to find out, though. I've tried to go down the road of connecting with the modeling centers to figure out exactly which profiles are and are not, or were and were not accepted. Making them available, as you know, making them available doesn't necessarily mean that they'll actually be picked up and used. But I believe that at least the technical aspects that had previously prevented the ARM radiosondes from being picked up by the GTS were addressed.
Okay, thank you.
Yeah, you're welcome. Any further questions?
This is Johnny. Just wondering if I mean, obviously we've got these model outputs for the atmospheric column at Oliktok. Do you think that is that something that your sort of group might be interested in looking at all as for this YOPP Site Nip? Because it seems like quite a nice data set to actually do some evaluation of the NWP systems.
Yeah, very much so. We're definitely interested. We're currently in a bit of an interesting phase. So I'm leading a site science effort for specifically for Oliktok, but kind of trying to transition to more of a broader North Slope perspective. And we're waiting to hear on the renewal status of that. But certainly if that goes forward and we have funding beyond this winter, that would be a primary activity for our group, is to leverage these observations to conduct model evaluation and improvement studies.
Because I mean, at the moment for this YOPP Site Nip, we're kind of I think a lot of the focus has been on sort of producing data sets for the first SOP. But if there was a more pressing need to provide the SOP2 data because somebody wanted to do some analysis of those runs, then it would obviously we could sort of try and put that up the priority list a little bit.
Okay, yeah, that's good to know. I do speak with Tennille quite a bit, so I'll also check in with her about that. But frankly, I think we'd be interested in either, but we do have this kind of enhanced data set for the second SOP specifically. So we have all of the other kind of the AMF3 measurements and the Oliktok measurements for the first SOP as well, and so that would be of interest as well. But given the kind of more detailed perspectives we have on the lower atmosphere from this campaign, it might be interesting to look at the second one specifically.
Yeah, sounds good.
Okay. All right, we are pushing past our hour, so I don't want to necessarily go too much longer, but if people have other questions about what I presented, please feel free to reach out to me directly.